washed through the vacuum filtration apparatus. Finally, the dry samples cool and weigh the final product. After this laborious process, the 3 process compositions are calculated, summarized, and concluded with the unknown number 137 containing 65.72 plus or minus 0.58%. You don't need 2 percentages here, percent sulfate. And so that's one abstract, and not everybody writes the same, so let's take a look at some other abstracts here. Let's see this abstract. To develop skills in weighing, washing, drying, and quantitatively transferring a solid. Now I'm beginning to think maybe that is a Wikipedia entry. They're just cutting and pasting parts of it, right? By using balanced equations and using statistical analysis of results, we use gravimetric analysis to determine the mass percent of a sulfate ion given in an unknown mixture. You don't have to make it sound fancy. Just something simple is fine, but this, in your own words, is better. I appreciate. Since this is the first report, I'm not. My expectations aren't super high for this. This experiment was done by weighing out 3 different portions of the unknown mixture and then dissolving them in a dilute HCl8Q. We warmed up the solution and added excess amount of barium chloride solution so that the sulfate ions would precipitate as solid barium sulfate. We then warmed up the solution until the barium sulfate was solidified. After we filtered off the barium sulfate in the solution and dried it in the oven to remove any water left in the barium sulfate, then we got a final reading using the analytical balance and calculated our average percent to be 64.2. This, get rid of that. It should just be 64.2 plus or minus 1.52% sulfate, something like that. One thing that's glaringly omitted here is the unknown number. I don't want to have to read the whole paper to get the unknown number. I just want to read the abstract and know what unknown number is. And so it's important that it contains that. Okay, let's take a look at another abstract. Let's look at this abstract. Average 46.0 grams by mass of sulfate was determined from 3 unknown mixture using gravimetric analysis, such as weighing, quantitatively transferring, washing, and drying solids, and balanced chemical equation and stoichiometric calculation using simple statistical analysis results. This is a bad abstract. This forces the reader to read the entire paper whether they want to or not, and most people don't. I'll tell you, most people would rather not read the whole paper. Unless it's directly applicable to their research, then they want every single detail which they can get from the paper itself. And so this is, as far as abstracts go, this is an F. No bullet points. Abstracts are single paragraph. I like this abstract. Although none of these abstracts are perfect. For example, rather than calling it solidification, they should have called it coagulation. Little details like that detract from the abstract. The purpose of this lab experiment was to determine the mass percent of sulfate in an unknown mixture. The unknown mixture was given to us was number 136, which was a white powdery solid. That's good. This is the first person to explain what the unknown even looked like. Right? The experiment was performed by putting 3 weighed portions of the unknown in a very dilute hydrochloric acid solution. Then barium chloride solution was added to precipitate all the sulfate ions as barium sulfate. The barium sulfate was then filtered and dried. The mass percent of sulfate was calculated from the mass of the dry barium sulfate. The average mass percent of sulfate in the unknown mixture was found to be 63.40 plus or minus 5.72%. And so this was pretty good. Except, did they say 3 samples? No, that's important to know as well. So, like I said, none of these are perfect. Oh, why? Because I want to know what the unknown number is, so I can check how close they were. And so, in the abstract, I'm going to be looking for your unknown number and your percentage to see were you close or not. All right, going back to this paper, they spent a lot of time on the introduction, and I think 0 time on the abstract. I don't know what, but a lot of time on the introduction, and I didn't check this, could have been because they just had a lot of information on Wikipedia or something. They just copied and pasted it in here. But you know, if it starts sounding like a Wikipedia entry, then I'm going to check it to see if it is indeed one or some other entry. But anyway, let's go here. Sulfate ion is a polyatomic anion with the empirical formula SO42- and the molecular formula 96.06 grams per mole. Is that a molecular formula? It consists of essential sulfur atoms surrounded by 4 equivalent oxygen atoms in tetrahedral arrangement. The sulfur atom is in the +6 oxidation state, while the 4 oxygen atoms are each in the -2 state. Its conjugate base is bisulfate. It comprises polar covalent bonds and ionic bond. It has double bond and single bond. Makes it to have 6 resonances. You know, we were doing Lewis structures at this time. Because of its chemical bond arrangement, it is a very radical crystalline compound. That, you know, I need a source because I don't know what a radical crystalline compound is, so I want to look it up, but there's no source given. Some of this I don't need a source because this is just from the book, you know, our textbook or lecture. Anyway, it is very reactive, and this should say hydrolyzes easily, and this makes it to have a highly chemical significance in our environment. And then it goes sulfates. What are some of the historic uses? So in the introduction, you either give a history, you know, of the technique, history of sulfate, or both. You know, you could talk about the analysis, the type of analysis when it was developed, that kind of stuff. Or you could talk about, you know, the application today. You know, how are we using sulfate commercially, etc. And so, actually, there's a lot of detail in here. It talks about vitriol salts, talks about batteries, deep sea, algaecide, therapeutic baths, plaster, cationic drugs, detergents, soaps, shampoos, fossil fuels. A lot of information here, but no sources were cited. You know, that's not good. Even if it's just from you know, Wikipedia, you should cite that, and you could use any citation format. It's fine. But look at this intro compared to this abstract. It's not really balanced, is it? And the intro goes on. Okay, following the intro section, and you know, most people's intro, I don't have that much time, but most people's intros were kind of similar. You know, gravimetric analysis, sulfate, so something about sulfate, something about gravimetric analysis, which is this technique that we use. This is kind of interesting here because they did some additional research, and they found, like Theodore W. Richards, you know, refined many of the techniques of gravimetric analysis. So that's kind of interesting. And this person cited something, gravimetric analysis. Let's go take a look at their source here. And we have something here. So that's good. And so they talk about that, and they talk something about sulfate, I think, here. Here, this is a different source, Holler, you know, gravimetric analysis, and then something about some sulfate here. And then sulfate from a sample uses the precipitation method where an unknown. Okay, this is what we did in this experiment here. This volatilization method and the precipitation method. And they're just saying in this experiment we did the precipitation method. That's good. That's good. Okay, after the introduction, which gives a little historical perspective, we come to an equipment list. No, we never want lists like this. You know, most journals, no lists are allowed. You know why? The journals, you know, there's a premium on space in journals, and this is a tremendous waste of space here. And so you'll never see bulleted lists unless it's critical to your point. And so this is a complete waste of space. And since thousands and thousands of copies are made, it just wastes a lot of trees in doing that. Instead, experimental details are always in paragraph format like this. Sometimes you could have tables, but the experimental details, you're telling somebody exactly how you did it. This whole paper is in past tense. And so we got to watch it. And so what did this person do exactly? And so here they're talking about drying and weighing out the samples, cooling in a desiccator, dissolving them. This is all just nuts and bolts. So you took 50 milliliters of this, added it to that. That's it. What you actually physically did without any kind of thinking. It's a cookbook style procedure. Inspecting for cloudiness, etc. That's the experimental section. So went on to filtration, drying, and then weighing the samples here. Take a look at this experimental section. Does this experimental section tell us, how much, what they mixed? No. This experimental section is bad. We want the details. Let's take a look at this experimental section. Looks pretty good. Oops, I'm blocking the camera here. Goes through. Experimental section is pretty simple to write. You just describe what you did in the experiment. Okay, after the experimental section comes what section? The results section. And the results section just summarizes some of the data. In the results section, you can have a table like this. Tables aren't a problem. Bulleted lists are the tables aren't. And so we have our 3 trials here. But there's one thing about the results section, and this person had it mixed up. They're mixing results with discussion. And so what's the difference between results and discussion? I'll tell you. The results section are just the facts of the experiment. The discussion section is your interpretation of the facts. And so here, this wasn't good, so I had to cross this out. Mass of crucible plus precipitate is 19.0637. That's a fact, right? It's not a fact that precipitate was pure barium sulfate, is it? No. And so here we do this. Is it a fact that your unknown sample 1 had 65.42% sulfate? Is that a fact? No, that's what your interpretation of the data led you to believe, but it's not a fact. And so the results section are just the facts. And then you analyze the facts in your discussion section. And the reason those are kept separate is because, different people might analyze the experimental facts differently. Not only that, as equipment becomes more and more sophisticated. Actually, you know what? I thought we were going to 4:30. We had time for a break. Do you guys need a break? No? We'll just keep going. We'll finish. Oh, this is good. I don't have to rush. I thought I was out of time. But I can talk a little bit more about the discussion. I had to rush this morning, so I ran out of time. So going back to this, what you see sometimes in the scientific literature is a paper that's titled like this. The title goes, "A Reinterpretation of So-and-so's Work." And so somebody came along, they're reading somebody else's paper, they looked at the results, and they had a totally different take on the results. Their analysis of the results conflicted with the author's analysis of the results. And so what they did was they published a paper, refuting the other person's analysis, basically saying that you guys analyzed it wrong. And so you didn't consider this or you didn't consider that. That often happens. And not only that, as things, as theory becomes more sophisticated, as computers get better and this kind of stuff happens, then, ideas about the theory change. Theories aren't static. Theories evolve, right? And so as those evolve, then, it's easy to reinterpret your facts. But the facts, will they ever change? The facts will never change. It's just how you analyzed it. There's a very famous story, since I have time, of the Lincoln Laboratories, at MIT. At the Lincoln Laboratories, there's one research team there that spent 15 years studying one series of compounds. It was like it's been a while. I forgot. My memory's bad. It wasn't the green LED. It was the blue LED, anyway, from yesterday. But going back to this, they spent 15 years researching this series of compounds because they had very interesting electronic properties. And all this time, they thought they were looking at, was it TiO2, all this time. But it turns out that their starting material, which they never check because it's a bunch of physicists. Chemists will always check the starting material to make sure it's pure, right? Before. Otherwise, you're kind of wasting your time if it's highly impure, because what you're going to form is going to be impure. Well, they never checked the starting material. They just looked at the bottle. The bottle said it was this, and so they used it. And it wasn't until much later that people tried to repeat what they got, and nobody could repeat it. And finally, since nobody could repeat what they were doing, so they started looking, okay, maybe the starting material. And so they analyzed the starting material, and it turned out to be highly impure. And so there are a bunch of impurities being doped in there. And so you would think 15 years down the toilet, wasted time, because all this time they thought they had something, which they didn't. But it wasn't a complete waste of time, because, the data was there. They just had to say, okay, all the papers that were published on this are no longer good. We're going to reanalyze the data now that we know what the composition is. And so that's a very famous story in chemistry. But going back to this, so we want to keep the results separate from the discussion. Now, the discussion is going to be your analysis of the whole experiment. We don't do that in the experimental section. In the experimental section, this is purely nuts and bolts. You mix the flour with the water. You don't care what the water or the flour does. You just mix it, right? That's experimental. In the discussion, we care. Okay, why are you mixing it? Why are you mixing it with that much water? This kind of stuff. What if we use less water? What if you use more water? We want to know this. So the discussion section is going to be the heart of your paper. And the discussion section is where most of the points for the formal report will be. And so let's take a look at this discussion section. Do you see this is a balanced paper? So here's page 1 of the discussion section. Single space, narrow margin. It's page 1. This is page 2 of the discussion section. Page 3 of the discussion section. Page 4 of the discussion, and a little bit more than 4 pages, which is kind of what you would expect for discussion section. This is considered short paper. A short paper, short paper would be less than 20 pages. And so short paper, you wouldn't have a conclusion section. A long paper, over 20 pages, you'd have a conclusion section you'd add on, right? And so short paper. Let's take a look at this discussion. How is this person's discussion section? Well, there's no discussion section. What do you think this person got? An F. Yeah, unfortunately. I think, I talked to them. They waited until the night before to do it. I was so busy with other stuff, so they didn't have much time. And so let's take a look at another typical discussion section here. So 1, 2, This one, they inserted results, so they're getting mixed up. 3, 4 pages. You could do this too, you know. Sometimes when the 4 pages is not that hard to write when you're including equations. You know, you not only want to include equations like this, how they got the standard deviation, you also want a verbal description of this. You just don't put the equations there, you talk about it, you know, in some text. You know, what are you doing at this point? Why are you doing it? Well, we need to calculate the standard deviation to get the lambda 95, right? That kind of thing. And you can see these, which are, you know, these papers overall are pretty strong. Some of them had some pretty big errors in it, but I can overlook some big errors if the rest of the paper is strong. But if the entire paper is weak and it's missing some critical stuff, then that's a problem. And so here's another discussion section. For example, this one had some. No, actually, this one. Let's see, 1, 2, 3, 4, 5. This discussion section is 5 pages long. It could have been longer, you know. But let me go back to this one, and we'll take a look. It's not the length; it's also what you say in there. And so, going back to this one had a major error in the discussion section. Do you know what the major error for me was? When I look at this discussion section, it bothers me that, okay, I see some algebraic equations there, and I see some verbal description of those equations. So, for example, to calculate the precision index, etc., to find the 95%, you got to calculate the standard deviation. This is all good, and these equations are good. I want to see those. But what is it missing? You know what is missing? I don't see one chemical reaction in that whole discussion section. You know, they talked a little bit about it, but to me that is a huge error, not to talk about the chemical reactions, right? This paper still got an A. So it depends. I mean, how I'm going to weight it. It depends on how strongly the other parts of the paper are. And so that's the way it's graded. Whereas if we look at this one, this is good. This person's including the chemical reactions, but this drives me crazy. They're putting the chemical reactions in the paragraph. No, what you want to do is and this takes up more space. It's okay to take up more space, but put the chemical reactions outside, you know, between the paragraphs, you know, so they're easier to see, easier to read. That's where we're going to take up. And so they took me too literally and not wasting space. And the other glaring errors, like this is totally wrong, you know, this statement here. But, you know, they still got an A because the rest of it was so strong, even though they had some serious misunderstandings of the whole thing. But, you know, they understood other parts of it quite well, and they showed it. And so that was good. All right, there are different styles of ending a paper. The style that's preferred in science is not to rehash. It's not to give another conclusion. It's not to restate what the percentage was. You know, when you end a paper like this, the concluding remarks are always going to be, you know, if you had this resource, or if you did this experiment again, how would you change it to make it better? Or, you know, what are some, you know, what are some problems with this? You know, it might not be a perfect analysis. There's still maybe some uncertainty in the back of your mind. So what could you do to alleviate that or make the whole thing better? Yeah. that's kind of what you do. And so you look, this concluding paragraph says nothing about, you know, the experiment. It just talks about, here's where you could have, you know, it doesn't have to be past tense. Here's where it could be future or present tense. Okay. And some references. All right, I'm going to stop here. So that gives you kind of an idea of what I'm looking for in the paper. And the discussion section is where you want to start. When you start the discussion section, do the calculations first. Figure out the standard deviation. Figure out the 95% confidence interval, and then start going through, you know, the steps. You know, because what people want to know is, how reliable is this analysis? You know, how confident can I be in that what you say is barium sulfate is actually barium sulfate? And so you need to go through and explain that you've thought of all the different aspects of the analysis, the weak points and the strong points of this particular analysis, and that you have everything covered. Okay.